well, it's Luka's presentation. I'll take a bit. You start.
Hello, everyone. We'll just take some pictures for our product managers who ask us.
Fabulous. Thank you.
Thank you. So, hello, everyone. My name is Lukasz Luba. I work for Redpath as a tech lead, and we are going to discuss some old known problem for our latency constrained scenarios. So let's go through the agenda. It's been a while where we introduced some different hardware, and we open up some new dynamics in this hardware, and the Linux kernel has evolved as well. And this is about the, so that would be the introduction for this talk, and then hopefully we can discuss more the proposed design, or maybe we could agree about some further steps how we can address those dynamics. So this is the introduction of the problem scope. We have basically talked quite a lot about the latency issues with different vendors and OEMs, and we also discussed this in recent days. It's quite common that engineers and the users, they experience some issues when they start interacting with the hardware. So this is mainly from the mobile world perspective, and you all know that we have some workloads which are quite sensitive to the latency, and we try to monitor the situation. We try to come up with some good, nice policies for that, but we still are missing some hints from the application, I would say. Yes?
Just one question to be sure. So in your first line, you say managing latency of device based on workload.
Yes.
The latency for the CPU at the CPU level, I mean, whatever is in.
Basically, any device. Yes, so let me clarify that. So the device would be a CPU, but also it can be the L3 level cache, which I will show you on the next slides, and or a bus,
yeah,
or
even the latency of the L3 just as a subpart of your CPU.
Exactly.
Latency.
Yeah, exactly. So this was kind of missed, and I will tell you why that was missed, because your L3 cache frequency or size will affect your IPC performance on your CPU, and this is something which is missed sometimes in those analyses. And this is the example of those applications that you can think of. Yeah, so there are some mechanisms in our existing power management subsystem which try to control, for instance, the DVFS or idle states, or suspend or resume mechanisms. And then we put more into those subsystems, sometimes without a consistency. So that's kind of, for the mobile phone, it's easier to manage like consistency, because we have limited number of CPUs or a limited number of applications running on the top app or the screen. And we also have introduced some hardware mechanisms which actually try to do similar things, but without notifying the Linux kernel. So there are some inconsistencies. Yeah, and this is about the evolution of our hardware. So you might remember some time ago there was a word which was quite simple. There was SMP processors and L2 cache shared. And basically, if you do some partitioning of those resources and you run the application, in most cases it was kind of easier. And then we introduced something like a big little technology, which was consisting from small CPUs and the big CPUs, little CPUs and the big CPUs, and they've been made from different cells. So those transistors, they had different characteristics, and some of the operating system, like Android, they leverage that new hardware because they built on top some mechanisms like C groups for the background tasks or for foreground task and top-up C group for what you see on the screen. And there were some assumptions that if you shut down some applications or if you turn off the app or turn off the screen, then you are likely to benefit from automatic magic hardware that you don't leak too much power. So that was a really nice design. And what happened later, it was something around 2016-17 when this big little architecture with those two private caches with L2 with different characteristics, they have been changed into something different. We have introduced L2 cache private to the core, and then we added L3 cache. And that was mentioned a few times during this conference. The L3 cache is quite important, but as you can see from this picture, it spans all of the CPUs. So if you have the old design from the operating system, some old applications, and you would assume that you would be more efficient, energy efficient, if you just tied the tasks into those little CPUs which have the little L2 cache. You would be good. But with this design, it's probably no longer true, because then you have the L3 cache, which is actually even bigger than the L2. And it's quite dynamic how that behaves. And you have problems with the leakage as well. You might have problems with the latency, how fast you can get the data out of this L3 cache. So the normal design, which was previous generation Android OS, might not fit well into this. And we've been doing some experiments back then, 2016-17 with Ionela, around this L3 cache, trying to come up with some nice policy. And the problem was that L3 cache size can change dynamically in time. So you basically can shrink this size of L3 to save the leakage, or you can expand this. And this is a completely new dimension. It's not only scaling the frequency of L3, but also scaling the size of L3. Back then, we've done this in the Linux kernel. There was a governor and the driver. We've been trying to figure out, based on some counters, what should be the size for your L3 based on your workload. That was 10 years ago. And now, that was actually pretty decent research back then. It affects your IPC, of course. And now there is this movement to put all of those algorithms into the firmware. So basically, you can slice the L3 cache vertically or horizontally. So this is yet another dimension. And you can slice, you can change the frequency. And the frequency will affect your response time, so latency, how fast you will get the data out of your L3 cache. So if you miss into L2, then you go to L3, and then it depends on that frequency if you get the data faster or not. So that would be driven in the firmware. And yes?
Do I understand you correctly that you said that the firmware can shrink the size of the L3 dynamically?
Yes.
Without notifying the...
It's up to the firmware. It's opened for, it's a part of the spec. You can check the public documentation for that L3. This is actually DSU. So if you read the DSU capabilities, then you can change the frequency. You can change.
I understand that you can change the size. What you're saying is that the firmware,
based on counters, yes. Without notification, based on those counters that are provided to this firmware, it can read those, come up with some metric, and shrink your L3 cache.
Yeah, it would turn off.
No, it's just that from a Linux scheduler point of view, it's quite difficult to make any decision if behind the scene.
Exactly.
But it affects all CPUs equally.
It affects all CPUs equally, but well, to some extent, Chris, because so there is also
as long as you only have one L3.
True. But so you can slice, you can shut down the cache. You can basically turn off some ways in the cache because that's just.
I mean, I understand that, but I would assume that if it's come from the OS to say, okay, now I know that I don't need all this large L3, you can shrink the size. I mean, that's you can manage that.
You might assume you would
you
link that
trigger
to some
it, so
sort of
Yes.
you're aware that the size has
it doesn't
changed.
work that way.
Now, if you are running and suddenly you lose
Exactly. So this is the
80%,
this is the main goal for this presentation.
How do we get the kernel to tell these things?
Yes.
Please stay out of my business.
Exactly. So this is the main goal for this presentation. If we can agree about something like the generic mechanism to say that I need this decent level of performance, or let's say latency. So don't shrink the cache, don't change the frequency of the cache because I know what to do.
But cache ways are controlled by resource control.
to say that the rest control
Yes,
compare.
CPBN.
It's not guaranteed. So yes, so the cache ways you can
Make sense to have double control of cache ways. So if you want to control cache ways, resource control is where you go.
for resource. So yes, we have this mechanism which is called MPAM. I haven't put it here. Jonela put it in your presentation. That was the MPAM. So yes, we can control the.
MPAM allows you to control it on a per transaction basis.
We would like something like the generic for not only the ways. So,
but they're all proportional on top of how much cache is available.
So there is also something. So that's why I started, but I haven't finished. So you can slice the cache vertically or horizontally. So you still keep the associativity, but you cut horizontally the cache. You can do this. This is yet another dimension. This is the partial shutdown, which we've been working on 2017. So you can basically do 3 different things: frequency, ways turn off, or the size from different angles. And this is something which might confuse people who trace applications because the utilization can grow. And there is no mechanism to say, please don't do this. Like you mentioned about this turbo flag. So there's nothing like, please provide me this stable environment. So that's
Well, when resource control is in use and you have assigned tasks to a group that explicitly use the full cache, that's a definite sign that you should not be disabling ways or cutting.
Right, and I think there's one more thing, right? You have to look at it in conjunction with and without the use of REST control. So that most of these mobile framework on devices today, they don't use REST control. So if you're not using REST control, then you do definitely land into this problem.
I think someone's disagreeing.
No, yeah. So, I mean, the ARM ecosystem is very wide, lots of vendors. Some of them will use, a lot of people will not use. And when you don't use that, it's probably still valid that you've got cache cut off.
Isn't it the other way around that nobody actually uses the partial power down, but they actually use MPAM?
no.
This power off is also an important feature requested.
It's used
Off,
MPAN and off together.
together.
but partial power down.
Yeah, partial power down.
Do you use that?
It is a highly requested feature.
Okay.
Can't it be done through the REST control anyway?
Ah,
At least you have one interface, the REST control, where you configure everything.
Very, very recently merged, though, isn't it, for ARM?
Sorry?
It's very, very recently merged for ARM.
Yeah, no, but otherwise that will be really tricky to understand who is doing what. If you can modify using the REST control when you have MPAM, and maybe another way if you want to do partial off in addition to MPAM, or if you have only, how you deal with that. And if you have only one entry point, at least you know that everything has to be set there. Then this can be split behind.
Right now, this doesn't get exposed anywhere unless a vendor wants to do something vendor specific.
So there's no like standard way of doing this. How about the frequency? Does this REST control allows you to set the decent frequency on that L3 or any bus?
Different frequency is different Java.
See?
Frequency
So-
is different, right?
Yeah, so we would like to have something like more abstract. Maybe I will go to
But
that.
resource control have available bit masking for the cache.
Hmm.
Bit mask. So bit mask is kind of mapping to the ways which are shutting down.
Yeah, and if you can do the half hashes, because that's I think how you implement the half thing, you can just double the way bit mask, and then
And you have 2 bits per slice. for example,
Something
2
like
bits
that.
per regular slice.
yeah.
So there is, on some platforms, there is frequency control for cores on the inference control. I think,
Possible to clamp in the frequency
yeah,
over there?
also, yeah, because this is just a different type of resource.
It is. It is.
From-
Yeah.
No, so in principle, you could use that interface to control it if you know, if it is possible to control it all. You know, but if it is, yeah, it could be added to that interface, I think.
So for now, the REST control is.
I don't know if you need to put the frequency scaling, the REST control, because that's another dimension, but we are speaking about the size of your L3 or how to partition that. And the
That's
REST
just
control
one.
look like
That's just
the
one piece.
interface.
That's just
So
one piece of one device. There's
We,
tens of these things.
the frequency here means the frequency of the cache.
Yes, I know, but I mean, there is, we have one dimension about how much of memory or cache you want to have access, which is one thing, just like you want a number of CPU or a number of, and then there is the other thing which is correlated, permanent, when you want to scale down, but we are scaling down just to save power, or at least to provide power to another thing, which is another dimension.
It's another dimension. Yes, I
But
agree.
that will never say I want to run slower. I mean by default.
Right.
It will say I want to run, and then we'll just deduct that you can run slower without any performance penalty.
Well,
I mean, normally everybody wants to run at highest frequency and the largest cache. It just because it's not sustainable, then you have to make some choice.
but it's
Are counter examples to what you are saying, so.
Because we have some power limitation, it's just because we have some other hardware limitation.
I don't know, so there are,
If we don't care about the max power budget, everybody want to run at max frequency. It's just because it's not sustainable and you will have to slow down something.
right, so, but the reality is that there is the max power budget and.
Yeah.
You need to take it into account,
Even
so,
even a 20 kilowatt rack has a max power budget somewhere.
yeah, there is always a power budget. And it is also the thing that you cannot just turn off sections of the cache randomly, right? You're probably looking at a few counters somewhere to say that the cache is underutilized, and then you collapse a few.
I mean, the
Like
algorithms
this.
generally would advise you to make sure the cache is not utilized before you turn it off, or you screw the performance over.
I mean, for the operating system to say I need less L3 cache seems a bit of a.
I don't think the operating system can say I need less L3. I think maybe the middleware can say I'm in a state where I expect not to run any apps for a
but,
while.
well, it depends. So, for instance, if we go back,
The free cache that we have available.
so there were cases. So, look, there was yesterday or the day before there was this Ricardo's presentation.
We have two.
Intel has this isolated island of tiny CPUs with only L2 and no L3, and this is something similar for us. We don't have that isolated island. We have this L3 cache.
We used to have the island.
There's now anymore.
Have you killed it?
You've killed. Ah, okay.
Either was that the application level,
to move.
Some entity decided to put things on the other power island.
Yeah. So in your mobile phone, when you are listening to music or something, then you don't need basically this large L3 cache, right? In the previous design, you could actually land on the littles, and then the cache was also tiny L2.
That's what you want to have. When you only had the shared L2s, the big shared L2 naturally turned off when
Yes.
used one.
The last big core was turning off the whole L2 cache cluster. And then you could just listen to music or whatever, you could just running. And that was by design of the hardware. Now you have this magic feature that allows you to do this, recognize this.
Really minimizes the penalty for migrating tasks around it.
Yeah.
Big L3, but
there are some pros and cons. Yeah, let me go further. So what we have, we are still in the evolution of that. So yeah, Linux kernel got some milestones. There was this big modification for the wake up path. We introduced this energy hour scheduler and energy model. And the main goal was to address, to leverage actually the big little architecture, which was good back then. We were not that much focused on the latency back then. Then there was another mechanism, uclamp, especially with the uclamp min. It's kind of artificial latency or prioritization mechanism, because the utilization of the task doesn't represent sometimes the need of that task. That's why we have this uclamp min, which tries to boost the utilization, and then it boosts the CPU frequency. But if the platform is not aware to boost the L3 cache or increase the size, then it falls apart. And yeah, so this is yet another example in this area where we introduce yet another mechanism to help with this. There was also the thermal load average introduced for the mobile phones because they've been suffering the throttling quite heavily. So conclusion. And we got this nice feature for the CPU frequency back then. That was the shared util governor, which allowed us to actually specify the needed frequency. So this is actually the counter argument what you said, Vincent. You've been working on that. Not always we are asking for the highest frequency. We might try to come up with some mechanism.
What I mean is that from a pure application of task point of view, they never ask us to reduce any CPU frequency and so on. We at the scheduler consider that the performance penalty is low enough that we can afford to reduce. Well, for that, we need to estimate what will be the task utilization so we can decrease the frequency without adding performance penalty.
I didn't
in itself, or the system will never.
Well, I didn't dare to put the uclamp max, but it's there. So we do this as well. So the uclamp min is there because it's less controversial. Uclamp max, I don't want to go into that gray area because we are lost. But we have some mitigations, let's say, you know. So yeah, we have a nice mechanism which actually can be used directly from the task scheduler, and then we manipulate the performance of that CPU hardware. But it's not automatically linked with the other performance bits, which actually are linked together.
Or already, you can already scale your L3 cache, you can already scale your DDR automatically, you can already scale your system interconnect.
From the schedule util?
Yes, in fact, with the lib, the OPP library, in addition to the CPU performance point, you can have some required change and you can have some minimum bandwidth requirements. So each time you set a new OPP level, that will increase the minimum memory bandwidth at the L3 or at the DDR.
So we are talking about static configuration. So like automatic linkage between the OPP from CPU and then OPP on L3 cache, interconnect, system level cache, and so on and so forth.
Yes,
that's like a baseline request to the platform.
But not always there would be such a need, right? Yes, we can start from that. Yes, thanks for the hint. To link OPP library to link those constraints. Is there any range that you can specify, or is it?
No, so far it's just you have a number of performance points where it's not only the CPU configuration, but that can be any performance domain. So I see my performance domain. So
Yeah.
that can be any interconnect configuration. I mean, you have a lot of things that you can add on top of that.
Okay. So yeah, I will probably fast forward to that slide. Yeah, so that's the evolution we actually discussed. There is also some CPU frequency PM/QoS that you would like to have some minimum provided capacity. That works quite well. So those improvements mainly went through the discussions where they were oriented mainly about the CPU frequency. But yeah, when you measure the utilization and then you actually see some noise, most of the engineers, they might forget about the LQ cache impact. And if it's there, then yeah, we haven't worked that much on this part. We've been aware since 2016, 17 that you might be hit by this, but we didn't have the control over this firmware. So those mechanisms, they were not like explicitly present in the Linux kernel. I'm not sure when the interconnect was merged with this framework, but before that, it was basically nothing to express even this kind of dependencies. Okay. Yeah, we had something like bandwidth control, but that was mainly for servers, for stable loads. So it was also kind of not the right interface to express such a.
I think there's an interesting conversation to be had at some point about CPU bandwidth at scheduler level and how we map it to a system level. Probably not today.
Not today, yeah. I just wanted to mention this. Same for idle state and wake-up costs. So mainly we've been focused on some CPU frequency and CPU resource, not the resource actually which sometimes provides the real IPC for that if you are constrained on the memory side. So yeah, that's why those caches, they were kind of left. Someone mentioned that it's part of DevFreak. But to be honest, there's
can be. It's,
yeah. You mentioned that
it can be part of DevFreak.
Yeah, this is what we have implemented in DevFreak. But
yeah, and it's been a vendor responsibility to control that. So sometimes it's DevFreak, sometimes it's firmware, sometimes maybe it's hardware.
We have released that.
No control over how that was implemented.
Yeah. So we have released that reference through the Linaro kernel back then. Some vendors, they pick it up from that.
And just took that and then something.
Yeah. But that was kind of modification to the DevFreak subsystem, which wasn't suited for that because we've missed the hinting mechanism. So you could react.
We still had to convert the cache utilization into some sort of fake utilization so we could use the on-demand governor.
Exactly. So there was some kind of on-demand governor customized heavily to figure out what is going on. But basically there was no direct hint from schedule that, the workload has changed. So the governors, like I think it was presented yesterday with this PID governor. It will learn from the past, right? But I need this frequency, so the task scheduler could figure this out, and then it would take a while for this completely autonomous system to pick the pattern. So that was back then kind of a solution. Yeah, you could observe the implication in your IPC, so lower IPC, for instance. So this is about the improvements for the rest of the subsystems. Mainly, as I mentioned here, this is the custom driver and governor trying to address the problem. Mainly out of 3, and then you would like to have some hint, for instance, from the schedule, sort of. But as you mentioned, Vincent, we might go through the interconnect.
So You have a new interface that you would like to discuss, or
So that would be the proposal. So if we can have something like you enqueue a task, and then automatically you actually notify not only one governor, like shed util about this new need, but then you populate this information further. Maybe that, maybe some other framework, maybe this interconnect framework, that something has changed, and now I have this need for this computation. Mean or normal utilization? Is it
so you can kind of do schedule till like predictive performance provision?
Yeah, instead of guessing,
Run this.
Yeah.
Instead of having to guess.
Instead of trying to guess or convert some counters to some threshold, like this governor yesterday, it has been addressing some problem which is actually understood workload, but in some more dynamic situation, when you would like to react like with uclamp min to the situation, then it's already too late. Sometimes for these interactive tasks, they are short-living, maybe sometimes 2 milliseconds or 3. So you might not pick up the pattern, but then if you have this kind of information pass through from the run queue, and then down the road, that would help the task to perform better in this latency domain. Word. Okay.
Actually, like the resource control, actually, each task, it can map into a resource control like task group. So that means when the task switched, then the context switch actually will let the resource control goes to a good partition, high priority partition. That means high bandwidth, high memory allocation available, something like that. Not in queue, but in the switch.
The switch.
It might, if you have the drivers set up to listen to it.
So there is actually no x86.
I think on ARM it pretty much just talks to npam.
Yeah, yeah. So there is a register which is related to the task switch.
We set the part ID.
Yeah, it contains all the information which resource control group the task belongs to, and
in the ARM hardware, that partition ID only goes with the memory transaction. It goes out of the
so there
CPU.
need to be some information that is at the task switch.
And then if you can combine the frequency as well with this rest control, that might be the interface. Or we can stick those two, the interconnect for the frequency, like the latency constraint.
So just from how you would like to express this latency constraint there? But I mean, is it because the latency constraint, there is a scheduler latency part, there is.
Yeah. So there are some existing, what you mentioned. To be honest, this is the front end of this framework, what you are describing. And I was hoping that Case would be here because he's working on this pelt manipulation and the higher layer. We are talking about the backend of this. So we would like to react on the information, the new one, maybe from this rewritten pelt or EVDF or something. So that's why we would like to align with you. So the upper layer, which is this latency expression of the task.
But the skid QoS, it's just that the goal to provide to the application a simple interface.
Yes.
Say, but then all the goal of this skid QoS library to translate an application request into
Bunch of systems, bunch of kernel parameters.
I mean, we have a number of kernel interface for the schedulers, which are almost never used. I'm pretty sure, for example, that for all the comparison that we've seen between EVDF and all the scheduler, I'm pretty sure that nobody play with the nice, the slice, and whatsoever, or the uclamp min and uclamp max. which in fact, this has been done in the SCADEX. I mean, they are doing that in their SCADEX driver because it's optimized, but nobody does that with the mainline user interface.
I see.
So what we want is to fill this bridge between user interface and what is already available. And once, I mean, if at some point we see that there is a miss in the interface, then we can express that this is missing. Why not add it? Right now, up to now, it was many people were asking for a new interface without explaining why the current ones were not enough. So we want to use the current one up to their limit to show, to highlight what is missing. And then we can have more, we can add some new interface.
Okay, so I was just trying to actually hook as a backend this functionality, because if you know that this is the latency sensitive information that you got from the user space, then we can help you with the rest of the system, because we know the system, but there are some tunings, well, configurations which are not managed properly, and you still might not provide this latency. Even if you express that I would like to have this task running super fast with decent IPC, you might still lack. So it depends.
So then, yeah, I mean, what has been the example that has been put in the email sent by Case is just an example of what can be used. You can extend that, I would say, to any interface that makes sense. It's just that we started with the obvious one.
Do we want to? Maybe this is not the place to have the. We actually want an interface where we can define classes from user space and just put application or threads in a class and then collect kernel controls in there to configure them for each one. That's kind of what Case is doing. Do we want to have the kernel controls and say, no, it's middleware's job to set them at the right times, or it makes a difference?
Yeah, well, so exactly. So that's why I wanted to avoid this controversial topic, because it's kind of the front end of this QoS. The backend is a bit more manageable. Like you have the resource that you can control, size or speed. Whatever you decide to do in this upper layer, it's up to you. But for instance, the uclamp min information, at some point, it's equipped with just a simple request to the driver. So when scheduled calls the frequency change, we then don't know if it was the real utilization or it was the boosted by the uclamp min. So this is lost, right? And for instance, if you would like to drive the cache, like, okay, so I have this low utilization, but somehow something has asked for higher frequency, maybe that's the time to also provide a higher frequency for the L3 cache. Or because the counter will not catch this up because utilization is low. You boost the frequency on the CPU, but you miss the L3. So the information is lost somewhere during that calling chain. And this is something that we would like to have, basically. So you can pass that information together, like uclamp min, passing the uclamp min. Then the counter will not catch this up, but the information will go.
On CPU frac driver, we have the SCAD policy where instead of providing one operating point, you have a mean and a nominal. And I know that SCADutil provide in this case the target capacity and the minimum capacity. That's what is used by Intel, if I remember correctly. So from the CPU frac driver, you can get the information, or maybe I don't know the.
And then if we hook this OPP from what you mentioned,
the OPP library?
Yeah.
Then the OPP library, I mean, just behind. Right now, the OPP library is just that set to value.
So the OPP library, we would just
everything that we are using, I think,
we would ask it for the parameters for this frequency. It's like a registry, is it, or is it?
So the primary thing here is that you need to know when to do those things.
Yeah.
Because that's, if you don't know that you did it, then you have to do it now.
Assuming the hardware is almost instant.
Well, so the uclamp min is kind of abused right now. So there are some services which set explicitly the uclamp min when they start, like the media server or Surface Springer. So those services, they know upfront that the uclamp min is the mechanism to just don't wait and provide the decent capacity. But so this is the known domain, the utilization domain, which actually it's not propagated down the road to those dev-freak devices. For instance, you know about this, the CPU can react on that. And then there are some there are some vendor hooks, maybe not plenty of them, but there are to hook something up like a bus or for you.
Right. So the basic problem to me is that when there is a task, switch to run, and it has utilization. Basically, don't know if this is real utilization or if this is something made up.
Yeah.
Because it needs some boost in some sense, and it may not be okay to propagate that information going forward.
Well, currently you don't have the mechanism to propagate.
Let's say we have one. You still don't know if this is real utilization. Or why would you?
So I would be interested in, so if the CPU frequency is higher and then the counters will not pick up the pattern because the utilization was low, so the transfer wasn't
fairly soon before we have a chance to catch up.
So, or let me rephrase, do we want to use utilization as a proxy for all the possible, for all the needs in terms of performance?
It feels wrong to use utilization.
It feels wrong. Yes. So that's why utilization is more about the throughput. That's my kind of impression. While we don't have anything.
I can imagine you might have some baseline fabric frequency settings based upon your CPU frequency. When you measure how fast various bits need to be to keep it satisfied, you might have configuration there. But that normally doesn't need to be exposed to the kernel at all. You can set those just in firmware because you've just changed the DVFS rail for the CPU anyway. So you know where it's gone. You don't have to expose those to the kernel. All the other, it's the stuff apart from the normal how fast it's need to go.
So currently the static configuration, it's not always the best. And there are some use cases where you can actually get a better performance or experience when you manually change those frequencies for interconnect, system level cache, and L3.
Right now, what we provide to schedule is the max and the target of the utilization. And then if you frac, it's just doing the max between util and boost, which is probably util and max. Yeah, it just take the max between the utilization and the min required utilization.
Yeah, so you can easily boost the frequency of your CPU. And then if you have this autonomous system in firmware which observes some counters, then it might be too late to pick up or even not even possible.
So that's the case in x86. We don't. Well, we mostly ignore whatever CPU frequency says anyway. And then we observe the recent obtained frequency and normalize based on that.
And what's the feedback from customers or users?
Because as long as it does the same thing every time, nobody even notices. If
it's consistent, right?
Yeah. But that basically means for this, like latency sensitive tasks, that's not translated at all, then, right? I mean, because they presumably if they're only like short-lived, then they're too
Yes, they are short-lived.
You
mechanism.
try and arrange the scheduling so that they wake up immediately after something that's run for a long time.
So is the problem that there are tasks with low utilization that really are
Quite important.
Yeah, utilization is
are
quite distinct from the
sensitive,
performance requirements.
sensitive, therefore they should run fast. So, and okay, so it is the one way to like provide that is to use uclamp.
Yeah, we can hook to uclamp main.
Okay.
Yeah.
What's missing?
Agreement that it would be abused this way as well. So if we can propagate this information further, for instance, to this, let's say this is the DEFRIC framework and governor. So the DEFRIC governors will respect something like uclamp min. So currently they have to respect suspend and resume, right? We set frequency that we would like to resume the device. So that would be probably yet another hook into that area. So instead of taking the metric that you have calculated, for instance, in this governor yesterday or day before with PID, take into account that, okay, there was a uclamp min as well. So ignore the calculation and set this frequency. That would be, Rafael, your proposal, basically.
Yeah, so I'm not sure if we agree that uclamping can be. I have no opinion actually.
Yeah, but this is currently only way of yeah. This is the only information that we have about latency need. Let's say.
Well, it is not information about latency. It's information about how fast the task is.
True. How fast I would like to go.
Should run basically because that's a
throughput request.
It's a yeah.
It's a throughput request.
Well, through performance. Let's just say, yeah.
For latency, at XNX we have things like EPP, right, and the SOC slider.
Yeah, but
it is a user who tells you how fast or how slowly you should ramp up.
so EPP is now standard. I mean,
Yeah. Does anybody know how to set it though? Or do people just randomly put numbers in it till it works?
the problem with it is that it's platform specific, right?
Yeah,
so
exactly.
If you use the one platform display, then it
Might work for this machine
the same way, yeah.
with this workload and then retune it.
But on x86, as far as I know, it's mostly about how fast you ramp up the frequency or how fast you drop the frequency, depending on.
My point is that if you want less latency, you can play with those things, what it is from
You can.
at the system level.
But I guess the problem is that we already exposed EPP to user space separately. And we cannot use it directly. It's hard to use it automatically from the kernel because you cannot override the user space setting.
Right.
We haven't done that yet.
But anyway, so if we agree, if we can agree that uclamp max
Uclamp min.
The uclamp min represents the or whatever utilization level we get in the schedule to govern represents the performance.
It can be assumed to represent the performance need of the system while that task is running.
Then we can
Anywhere
use
we
this
are.
to propagate that information to other pieces.
In different frameworks. Okay.
Yeah.
Well, that will be a good information because then we can continue in cracking at LPC.
Yeah. We can have a hack around.
Just one note, because we handle this correctly in SUGOV, but let's say you also do it for like a thing, and there's a notification that's only active while queued in the run queue. That might not be enough because let's say you run for 10 microseconds.
You're gonna have non-sleeping. You're gonna have non-sleeping listeners and stuff.
Yeah. You need to hold it for a while because
Oh, I see.
it takes a while to take effect.
Well, so this is kind of implementation detail. If we agree to go that path, then we can talk about the implementation V1, V2, V20.
So I guess the ask for everybody would be to think of counter examples in which the uclamp may not suitable for
They will be.
over the coffee break.
Yeah,
Yeah, during the coffee break, because I think
Right.
so.
right, at the moment, I don't see any, but, you know,
Okay.
it might be,
It's a good sign.
You said that services have used the UFAM feed,
Yes.
right? Not that the counterexample.
Well, it's a trusted middleware, right? It's a media server, for instance. So it's
You can tell them that the meaning is slightly different and given sufficient time to get fixed.
you know, so the slightly rephrase what I just said is like, if you can think about a situation in which the utilization, either actual or artificial, cannot be used as a full information of the performance needs of the task, then that would be a counter.
I'm thinking about combining this with something on a CPU freak side that will turn it down when memory bandwidth indicates going fast, it goes no faster. But we can still pass the signal on.
well, we still need some driver like to poke the CMI for the caching
That
bus.
is already there, I think, because the utilization is scaling variant.
Yeah, the scaling variant, it comes into the driver. The driver can do what it likes and pass on the.
And because it is scaling variant, that it should react to the cases in which something is memory bound.
Yeah.
Because then
Well, it gets higher when something's memory bound. You spend more time
variant than it does.
No, but you spend more. You
No, because
spend more.
It's because of the pelt. So it's
You have 10 cycles, but you're still running.
you are running and you don't get data. That's why your pelt is noisy.
It runs at the same
It
workload
depends.
rate, but it uses more cycles.
So that's why sometimes the tasks is that size and sometimes it's bigger because actually the magic for your entry cache reacts.
Yeah, so it looks bigger.
Right, shall we continue?
Yeah, let's carry
Yeah.
this.
Okay. Thank you.
on the-
Thank you.